Welcome to this lecture series in real analysis. In this lecture, we'll be discussing Taylor's theorem, and let us recall some relevant material. So we'll need Cauchy's mean value theorem, which has been stated here. We'll also use L'Hopital's rule, even though the proof of L'Hopital's rule was just a simple application of Cauchy's mean value theorem. The precise statement is here, and we will need to know about polynomials. So let me just recall the definition of a polynomial, and I have written the precise statement, so let me not waste time on these two things. I have no philosophical remarks to make there. So what is a polynomial? Well, a function of this sort is called a polynomial if there exists. So this is a polynomial if there exist real numbers a naught up to an for some n such that f of x is this value for all real numbers x. That's the definition. Alright, so with that, let us proceed. Here are some problems for practice. And now let us get started. So first we will talk about higher derivatives, and to talk about that, let us see a motivating example. So first we will define a function from reals to reals in the following way. So f of x is squared if x is non-negative, and minus x is square if x is negative. And it will look something like that. My drawing is not great, but it will look something like that. Now, the question is f differentiable? And if yes, what is the derivative? What is the value of f prime at each x? So clearly f is differentiable at every positive x and at every negative x. What about x equals 0? Well, we just need to talk about right and left derivatives. And if you just think about it, the right derivative, which we denoted like this, at 0 is 0, because what is it? This is equal to f of, or rather, it is the limit as x approaches 0 from the right, fx minus f0 divided by x minus 0, which is this limit, which is 0. Let me not belabor the point. It is 0 because this cancels out, and that limit is 0. Similarly, the left limit will also be 0. So we see that the derivative at 0 exists and is equal to 0. So now we can write what is f prime. F prime of x is 2x if x is positive, 0 if x is 0, and 2x again if, or rather it is minus 2x if x is negative. Right? The derivative of this guy is 2x and this guy is minus 2x. So what is the graph of f prime? F prime is a bona fide function from reals to reals. What is the graph of f prime? So since we know the exact definition, the graph is this. Again, my drawing is not too great, but I'll try my best. So this is what f prime roughly looks like. Maybe I'll have a darker line. Yeah. Right, so that is the graph of f prime. 2x minus 2x and 0. So f prime is continuous but not differentiable itself. F is differentiable. F prime is continuous as we see, but f prime is not differentiable. So we need a definition to ensure or to demand that f prime also be differentiable. And then we can talk about the differentiability of the derivative of f. Right? We can keep asking these questions. And Therefore, we have a notion of higher derivatives, which we now make precise. So fix an interval, and just for the sake of understanding, keep that as an open interval. That's the easiest to psychologically keep in mind. You can also take this to be the entire real line for the sake of understanding. All right, so we say that a given function, so yeah, we also need a function. So let f be a function. Okay, so we have an interval I and a function defined on it. We say this function is 2 times differentiable if, first of all, if f is differentiable everywhere, that's 1 times differentiability, and f prime is also differentiable everywhere, right? So if f is a differentiable function, f prime is again a function from the domain of f to the reals, and we can ask for its differentiability. If that also turns out to be differentiable, we call f 2 times differentiable. In the previous slide, we just saw an example of a function which was differentiable 1 time, meaning it was differentiable, but not twice or not 2 times differentiable. So 2 times differentiable will also be referred to as twice differentiable. So pretty simple definition. We will look at an example, but I'm sure you can cook up your examples immediately. The constant functions are one such things. All right. The second derivative, suppose you have a 2 times differentiable function, then the second derivative is denoted by, we write f and then put a double prime. So f double prime of x is the double derivative of f at the point x. So just to be very, very clear, what this is saying is f double prime of x is the derivative of the derivative at x. This is a function. It is also a differentiable function by hypothesis that f is 2 times differentiable. We can talk about its derivative and take the value of the derivative at x. All right, I'm sure you've seen this in high school physics. Similarly, we say f is n times differentiable, where n is any positive integer, if f prime, meaning the derivative of f, so first f is differentiable and f prime is n minus 1 times differentiable. So f is n times differentiable if, first of all, it is differentiable, which I haven't written, but it's implicitly there, and its derivative is n minus 1 times differentiable. So the definition is inductive. Suppose you write a 3 here, then what are we saying? F is 3 times differentiable if, first of all, f is differentiable and the derivative of f is 2 times differentiable. When 2 times differentiability we have already defined. So this definition is inductive, but okay. And 1 times differentiable is same as differentiable, that we have said. All right, so what is the notation for the nth derivative? So what do we mean by the nth derivative? Well, you take the derivative of f, it is a differentiable function, you can take its derivative, then it is a differentiable function, you can take its derivative, and you can do this n times. But of course, this is not a good notation. Or we can maybe try putting n dashes, but even that is not a good notation. So we have another notation, which is this. This is how we denote the nth derivative, and again, maybe I'll write it in pink. This is how we denote the nth derivative, and just to be very clear, the nth derivative is the derivative of the n minus 1th derivative. All right. And maybe one more remark I'll make. The second derivative, f double prime, f double prime is nothing but this thing, just a notational remark. All right. Finally, we say f is infinitely differentiable if f is n times differentiable for all positive integers n. Such functions are also called smooth functions. So infinitely many times differentiable is same as smooth functions, just another terminology. And examples, polynomials. You take polynomials. All polynomials are smooth, meaning they are infinitely differentiable. So they are certainly 2 times, 3 times, 5 times differentiable and so on. Okay, and you can cook up your own example. Talk about surds, for instance. What about these guys? Are they infinitely differentiable? Think about that. Okay. So what is the motivation or the idea behind Taylor's theorem? Taylor's theorem is an attempt to understand a given function, a sufficiently nice function, in terms of polynomials. Meaning, it talks about polynomial approximations of a function which is sufficiently nice. We will talk about what is meant by sufficiently nice. And polynomials are a particularly nice class of functions. So if you have a handle on a given function in terms of its, in terms of polynomials, then you can maybe answer a lot of questions about it. So anyway, so let's begin at least the first step towards Taylor's theorem. We have a function f defined on all reals. Soon we will relinquish this entirety of the reals as the domain. So just for the sake of understanding, we have taken all of the real numbers as the domain. So we have a differentiable function defined on all reals, and a is any fixed point. So a is a point in the domain. F of a is the value at a, obviously, and then what we are attempting to do, or what we already know, is that the value at a plus x can be understood. First of all, you have the value at a, and then what is the error? If you subtract f of a plus x with f of a, you have an error. So think of it as trying to approximate this value, the thing that you wanted, with what you knew, but then you will incur an error. And by Lagrange's mean value theorem, we know that the error is of this form, where Cx is some number strictly between 0 and x. So there is some point strictly between a and a plus x. Cx is strictly between 0 and x is same as saying this point is strictly between a and a plus x. So there is a point strictly between a and a plus x such that the slope of the tangent line at that point has the property that if you multiply that slope with the difference in the x coordinates, you get the error. So this is the error. This is the difference between f of a plus x and f of a. That error is same as the slope of slope at a suitably chosen point multiplied by how much you travel in the x direction. Right? You just take this line and translate it to make it tangent, and you will find such a point. So this is immediate from Lagrange's mean value theorem. And think of this as a first order approximation of f of a plus x. This is your first order error, whatever that means. This will be clear or more clear in the next slide. So the next slide attempts to, so this is what I just said. Think of this thing as the first order error. E1 is denoting the first order error, and the question we are considering is, can we get a higher order polynomial approximation of f? This is in some sense the first order polynomial approximation of f, in the sense that this is your first order error. If you had a more stringent hypothesis on the function, here we only assumed differentiability. Suppose we had the knowledge that the function is many, many times differentiable. Can we do better? Can we have a better polynomial approximation to the function? So let's see. So this time again, we have a differentiable function. We have a point a fixed in the domain. And then we want to understand the value at a plus x in terms of the value at a, the derivative at a, and then our error. So let's see. So we write f of x, or rather we write f of a plus x as f of a plus x is written as the value at a, the value of the derivative at a times x. So this is sort of your polynomial, but then you have an error term. So this error term is multiplied with x squared. So this is therefore called the second order error term. So this is f of a. Then you have f prime a times x, which is this much, right? The slope of this line multiplied by the distance you travel in the x direction gives you the distance you cover in the y direction. So this is f prime a times x, and this is your error. So let me write that. This is e to x times x square. And what we want to do is we want to understand e to x in terms of the derivatives of the function f. And we have assumed twice differentiability this time. So yeah, so this is the question. What can we say about the second order error? And to do that, first we will write e to x as, just by basic algebra, we write it like this. These lines are never horizontal, and that bugs me to no end. Give me 1 second. Yeah, hopefully this is horizontal. And yeah, this is divided by x squared. So this is true for all x non-zero. So that is our second order error once you choose a non-zero x. Okay, so define, just for convenience, define phi of x as the numerator. What have I written? This complete garbage. Yeah. So define f of phi of x as the numerator. Okay. So e to x is therefore phi x divided by x squared. Now this we write as phi x minus phi 0 divided by x squared minus 0 squared. So what happened? Phi 0 is 0. If you substitute x equals 0, this cancels out, and this is anyway 0. So phi 0 is 0, therefore we can write phi of x as that, and of course x squared can be written like that. So now we are in good shape to apply Cauchy's mean value theorem, and by Cauchy's mean value theorem we get this is equal to phi prime c divided by the derivative of the squared function at c. So that's 2c for some c strictly between 0 and x. Right? So what is phi prime c? Let's calculate phi prime c. So by definition of phi prime x is f prime a plus x minus f prime a immediate. So phi prime c is nothing but this expression, this divided by 2c, but let us isolate the 2 and write it this way. So just note that this is equal to that. And where is a plus c? A plus c is strictly between a and a plus x. So it could be somewhere here. C was strictly between 0 and x. So a plus c is strictly between a and a plus x. Now just look at this expression, and here we can apply Lagrange's mean value theorem, which is a special case of Cauchy's mean value theorem. But since f prime is a differentiable function, here we can apply Lagrange's mean value theorem to write this is equal to the derivative of f prime, which is f double prime, a plus d. Yeah, just that much. So this is f double prime a plus d and a half, of course, for some d strictly between a and a plus c. Sorry, so for some d strictly between 0 and c. Right? Immediate from Lagrange. So f prime is just some differentiable function, so I don't know how else to explain this, but this is a direct application of Lagrange's mean value theorem. There is a suitable d in this range such that this expression is that expression. So a plus d is strictly between a and a plus c, so it could be somewhere here. So the second order error term looks like half of the second derivative at a point strictly between a plus x and a. So that is the second order version of Taylor's theorem. So we can write the second order version of Taylor's theorem as f of a plus x is f of a. I don't know if I should write that there, but let me write it here. F of a plus x is f of a plus f prime a times x plus the error term, which is half of f double prime. Let me write a c here. F double prime, maybe c is overloading, maybe let me write a xi. F double prime xi x square, where xi is some point between a and a plus x. So all of this reasoning, whatever we did here, proves this, that f of a plus x can be approximated by a linear term, by this is like a polynomial, first degree 1 polynomial, and then the second order error term, which looks like this. Let's see the third order version, and then we will state the general version. So this time, again, we have a function from reals to reals, which is thrice differentiable. A is a fixed point in the domain, and we are asking, suppose we write f of a plus x as that. So this time, f of a, f prime a x, and half of f double prime. And this half this half should now look motivated because of the previous, the second order version. In the second order version, the second order error had a half here and then the second derivative at a suitable point. But here we have changed that suitable point to the point A itself, and the third order term will, we have to talk about this thing, the third order. So what can we say about E3x? So just like in the previous proof, we write E3x as, by basic algebra, this is this whole thing divided by x cube, and this is for x non-zero. Okay, so we want to comment on E3x in terms of the derivatives of the function. And again, just call this numerator as phi of x. And I don't want to write a separate line for it because I'll run out of space very soon. So this numerator this is phi of x. So E3x is phi x upon x cubed. And once again, phi 0 is 0. Right? Phi 0 is 0 because these two things are anyway dead at x equals 0, and these two cancel out at x equals 0. So by Cauchy's mean value theorem, this is phi prime c divided by 3c square for some c in the range 0 and x. Right? But what is phi prime c? Phi prime c is f prime a plus c minus f prime a minus f double prime a times c divided by 3c square, but let's isolate the 3. Okay. Now look at this expression, and this is psi of c. So yeah, so this line is not horizontal again. Right. So this numerator will be called psi of c. So the numerator is psi of c, the denominator is c square, and psi is a function. At any point x, it takes the value, or let me say at any point y, it takes the value f prime a plus y minus f prime a minus f double prime a times y. So psi is a function defined that way, and at C it takes this value, and psi 0 is 0 again, because this term it will go away at 0. So again we will apply Cauchy's mean value theorem to get this will be psi prime at D, where D is a point strictly between 0 and C. So this will be f double prime A plus D minus f double prime A divided by 2D and times 1/3, where D is a point strictly between 0 and C. Right? Whatever we did here, we are just repeating that step. Instead of x, we see a C. Alright, and this 2 again we isolate separately, so that 2 comes here. And this time we can again use Lagrange's mean value theorem, a special case of Cauchy. So this will be f triple derivative A plus, let me not use E but something, let me call it H. H is also bad, I don't know, some number, let me call it E. Bad, but what can I do? So this is 6. E is strictly between 0 and D. So the third order approximation becomes f of A plus x is fa plus f prime A x plus half f double prime ax square plus not 1/3 but 1/6 f triple prime xi x cube, where xi is a point strictly between A and A plus x. Right? If you just follow where is E, E is strictly between 0 and D, D is strictly between 0 and C, C is strictly between 0 and x. So where is A plus E in particular is strictly between A and A plus x. So the third order approximation looks like this. And Taylor's theorem just generalizes this to nth order approximations. The general theorem is the following. We have some non-negative integer, I is some open interval. You can relax this also. You may not necessarily have an open interval, but let me just state it for open intervals. Fix some point in the open interval and fix a function f on the open interval, which is n plus 1 times differentiable. Then you can, for any x in R such that A plus x is also in the domain, you can think of this as all real numbers for the sake of understanding, but for any real number x, if A plus x is also in the domain, the value of the function at A plus x is, first you have a degree n polynomial, and here you see factorials appearing. I will define factorials if you don't already know, plus the n plus 1th order error. So the n plus 1th order error is this much. You have the n plus 1th derivative at a point C divided by n plus 1 factorial, or let me write a xi because I've been using xi so far. There is a xi here for some xi strictly between A and A plus x. So what is factorial? When we write n factorial, we mean n into n minus 1 into n minus 2 up to 1. So just like when we were doing third order, we saw something like 3 times 2, and you can always multiply by 1. So that was 3 factorial, which was 6. That's why the 6 was appearing. Okay. So this is something that you can just prove by repeated applications of Cauchy's mean value theorem, which we saw for the degree 2 and the degree 3 examples. There is no point me repeating that proof here because I'll be just using induction and the exact same ideas. No new ideas are needed. So this is Taylor's theorem, or rather this is the Lagrange version of Taylor's theorem. This is due to Lagrange perhaps. But anyway, this is called the Lagrange's version of Taylor's theorem. Lagrange form. Later we will see another form when we will discuss integrations. So yeah, so this is Taylor's theorem. I hope this was well motivated and this will be very useful. We'll see applications or at least one very nice application in the next lecture. As usual, like, comment, share, subscribe, and I will see you next time.